Explaining problem 5.2. So in 5.2, I treated the system as a first order process that relates a change of the heater power to the change in the temperature, and then the function we used that showed the temperature response depended on the two key parameters. And then I first identified the steady state changes. The heater caused the temperature to rise from 100 to 500, which is a total change of 400. The corresponding change in power input was 1. Using these steady state values, I calculate the process gain by dividing the temperature change by the power change, giving a gain of 400. And this gain tells me how strongly the temperature responds to power impact once the system has fully settled. Next, I found the time constant by using the first order response equation for the temperature. Since the temperature response follows an exponential curve, I substituted the given temperature value in at a specific time. This gave a time constant of 2.89 minutes, which represents how quickly the system responds to changes physically. It tells me how long the system takes to reach about 63% of the final temperature. In part B, I focused on how fast the temperature changes with time. For the forced order system, the maximum rate of change occurs when the system has been responding long enough that the exponential term no longer dominates. Multiplying the gain by the ramp given a maximum temperature change rate of 200 per minute, I also estimated that the behavior would be reached about 5-minute constants, or roughly 14.4 minutes. Overall, this problem showed how gain and time constant both affect it. And then for 5.4, which is a problem I kind of struggled with, I analyzed the first order system responding to the input rather than the step change. The transfer function indicated that the system has a gain of 4 and the time constant of 2. I wrote the concentration response for this step input using the standard fit. This gave me an expression showing the concentration rising towards a steady state value as time increases. However, the problem does not say how this stays forever, so I had to just kind of imply that, which kind of started to confuse me and how the limited time. So then I removed the at t equals 2 to model it correctly. Next, determined when the concentration reaches its maximum value. Because the input is removed at t equals 2, the concentration stops increasing at this point. Therefore, the maximum concentration occurs exactly at t equals 2. I evaluated the response at the equation at that time to calculate the maximum concentration, which came to about 5.05 moles per liter. And then finally, looked at how the concentration decays over the maximum. Once the feed is removed, the system follows a simple exponential decay governed by the same time constant. And then I solved for the time at which the concentration drops.